Okay. So I ended up in my last lecture at the definition of fundamental group. And what was that? That is, if you take a space, X be a space, and just consider one point in the space X, then you define loops based at X naught. Loops means that begins and ends at the same point, that is at X naught. That is, yeah. So this is X naught. So I am considering the loops at X naught. And with respect to the loops, we are to consider the path homotopy classes of loops. That is, if F be a loop at X naught, then we consider the class. What is that? That is the set of all those loops based at X naught which are path homotopic to that loop. And if you consider all such path homotopic classes of loops based at X naught and denote the set of all these path homotopy classes based at X naught by pi 1 x comma X naught, then pi 1 forms a group with respect to the product operation star that I have defined already in my last lecture on path homotopy classes of loops based at X naught. So this forms a group with respect to the product operation star on the set of all path homotopy classes of loops that based at X naught. And this group is defined as pi 1 x X naught is defined as the fundamental group of capital X, of the space capital X based at X naught. Yeah, fine. So for a given space and for a given point X naught, you can always have this group, fundamental group of X. So that means we are blending the topology and algebra together to get rid of the problem to distinguish spaces. Now, for example, just look at the simple space, that is, suppose we are considering the n-dimensional Euclidean space Rn, n-dimensional Euclidean space. Then what will be the fundamental group of X of Rn with respect to a point in the space? So suppose if you consider some x naught and f is a loop at x naught, based at x naught. That means this one. So you are living in Rn and you consider a loop based at x naught, then what will happen? Then you always have the straight line homotopy in between points of the loops and this point. Yeah. So the straight line homotopy will be the path homotopy between this loop and the constant path at x naught. So f is path homotopic to the constant path at x naught. So that means, so every loop based at x naught is path homotopic to the constant path x naught, which implies that its fundamental group is the trivial group. That is just consisting of the path homotopic class of the constant path at x naught. Yeah. And the same thing will happen to the space Dn. And also, if you look closely, the fact is that these spaces are convex. So if you consider a convex subspace in Rn and a point in that convex subspace, then with respect to this point, the fundamental group will be the trivial group. Okay. So these spaces have the fundamental group as the trivial group. But we are looking for a space which will have a non-trivial fundamental group, right? So before that, before going into that discussion, we need to discuss some basic things that will lead to that construction. Okay, fine. Now some questions, some natural question may arise that whenever I define the fundamental group, I am always specifying the point x naught. So that is the question you may ask, that whether the fundamental group depends on the point that we are considering. So let us have a look at the following observations. That suppose, okay, suppose you have a path, be a path in x from a point x naught to x1, sorry. Suppose you have a path, so suppose this, yeah, so this is x naught to x1, so you have a path alpha. Fine. Then with respect to this path, so you can always define a fundamental group at x naught and at x1. And in between these two fundamental group, you can set up a map with respect to this path. What is that? So how to define this? So suppose you are to consider a loop, a path homotopic class of a loop sitting at this group. So suppose you have f, then you need to have a path based at x1 with respect to this f and alpha. So how to get that? Okay, so you first start at x1. So what will be the path? So x1, so since alpha is a path from x0 to x1, then you can always define the path alpha bar, which is alpha 1 minus t. So that will be the path from x1 to x0. So this is the path. So going from x1 to x0, and then you go from this one and then get back to the family. Then you will definitely have a loop based at x1. So the definition of the map will be, so alpha bar plus star f star alpha. Fine. Okay. So this map can be easily checked that, so this is well defined. And this map maps the fundamental group of the space X at x0 to the fundamental group of X at x1. Okay. So let me have a look which properties this map has. So first of all, if you consider two path homotopy class, then what will happen? Then this will be, so alpha cap of this is something like that. Okay. And this one is, yeah. So now, by using associativity of this operation, you can have this one. Yes. So it is alpha cap of this. So this says that alpha cap is a homomorphism of groups. So alpha cap is a homomorphism. Fine. So thus, just if you have a path from x0 to x1, then you can set up a homomorphism in between two fundamental group on the respective points. Now, if you check, you can also have these facts, that is alpha cap is 1 1. Yeah. And alpha cap is a surjection. So these are your exercises. Yeah. So thus, if you have a path from x0 to x1, you have constructed an isomorphism in between the fundamental groups at their respective points x0 and x1. So hence, this proves that these two groups are isomorphic. So that is, if two points are path connected, so then at their at the points, if you define the fundamental groups, then they are isomorphic. So that means, so it says that if you are having a path connected space, then phi 1 x naught is isomorphic to phi 1 x x for all x. This. And more specifically, if you consider any space x and a path component, suppose P be a path component of a space x, and suppose x naught belongs to P, then you have the yes, the fundamental group of x at x naught is isomorphic to actually the fundamental group of this. So it seems to us that the fundamental group x at x naught depends on only on the path component of x containing that point. So that is, if x is path connected, then all the groups are isomorphic. But so there is a little error in thinking that that we are identifying all these groups with one another, and simply we are speaking of the fundamental group of a space x without referring to base point in a path connected space. But this will lead to a error, as there exists no natural way to identify these two groups, the fundamental groups of x at x naught and the fundamental group of x at x1, because different paths, suppose if you define two paths in between x naught and x1, okay, so suppose if you define alpha and beta be two paths from x naught to x1, then you see that for a path homotopy class of a loop f with the fundamental group of x at x naught, this equation yes, if we assume this one, then what will happen? Suppose this f satisfies this one, then just this will be equal to this. Then just okay, just doing a simple calculation on that, you will have actually this one. Yes. Which implies that this is alpha cap of this and this is beta cap of this. So this proves that, so for those path homotopic classes, the functions are same. So this proves that alpha cap, the map alpha cap is independent of paths if and only if for any path beta from x0 to x1, this class actually in the center of that group. Yes. So with this observation, I leave it to you to check that alpha cap is independent of paths if and only if the fundamental group is abelian. So I would like to note down that alpha cap is independent of paths if and only if the fundamental group phi 1 x x naught is an abelian group. Okay, fine. So now I move to define, as I have already seen that the spaces Rn, Bn or any convex subspace of that spaces, you have already calculated the fundamental group, that is a trivial group. So these spaces can be defined as, in general, that is a space X is said to be simply connected if it is a path connected space and if in addition to this the fundamental group of X at some x naught is the trivial group. Is the trivial group, which will be denoted as this. Now, since it is path connected, so you can calculate one of those groups. Then they are isomorphic. So phi 1 x x naught is the trivial group, and then you define the space as simply connected. So the spaces, as I have already discussed, having the fundamental group, the trivial group, are simply connected. And it should be noted that we have came across in complex analysis that in the Cauchy's fundamental theorem that if you have a region G and two paths gamma 1 and gamma 2 which are homotopic to each other, then their integrals are same. So okay, so let if you have two paths be two paths from x1 to x0 to x1. Yeah. Suppose you have two paths in a simply connected space. Then we see that the alpha star beta bar. What is that? That you start from alpha from x0, then you go to that x1, and then come back to this x1, this one. So alpha star beta bar is a loop based at x0. So since it is a simply connected space, so its fundamental group is trivial. So this path is this loop based at x0 is path homotopic to a constant map. A constant map. That means it is ex0. That is the class of this is actually a class of ex0. Yeah. So now just multiply both sides with the class beta, you will have this. So this proves that if alpha and beta be two paths starting and ending at the same points, then they are path homotopic. So this proves that alpha is path homotopic to beta in a simply connected space.
Sir?
Yes.
Sir, what if we take that alpha star beta bar loop based at x1?
Yes.
Sir, we can also take it as a loop based at x1, no?
Which one?
This loop alpha star beta bar. Yes, sir.
No, this alpha starts at x0 and then ends at x1, then beta bar starts at x1, then coming back to x0. So,
Sir, if we
yes.
if we take beta star alpha bar, then
Beta
if we
star,
take at x1 alpha
yes,
bar,
yes,
then it will be a point around in x1, right? Like we are doing it for x0, but then it will be for x1.
then it is
Is it
a
true?
loop at x1.
X1, yes.
But you are living in a simply connected space. So its fundamental
Yes.
group is trivial. So the same thing will happen. Right?
Okay.
Alpha is path. Actually, what I mean to say is alpha is path homotopic to beta in a simply connected space. Yeah. Okay, fine. Okay. And I have also talked about the examples of R2 and R3 at the beginning. So that is, if you take out 1 point from R2 and 1 point from R3, then R2 minus that point is not simply connected, but still R3 minus a point is simply connected. So that we can prove in later. Yeah. So actually, to compute fundamentals group, we need to go in. We have two directions. That is, one is that fundamental groups. That is, one way is to define covering spaces, and another one will be deformation retracts. If I get time, then I will talk of these two things. But definitely I will cover covering spaces. Yeah. Okay. So now, for any space X and a point on that space, you can define a fundamental group. But the thing is that our aim is to show that the fundamental group of a space X is actually a topological property of the space. Because if that thing is not correct, then the machinery that we have developed will go in vain. So that is our aim, that the fundamental group, so our goal is to show that the fundamental group of a space X is a topological property. Topological property. And Shoumo in yesterday, he was talking about complete topological property or complete invariance. So that was another interesting thing. So now we are concentrating on this. That is to show that the fundamental group of a space X is a topological property. So to achieve this, we need to introduce the notion of homomorphism induced by a continuous map. That is, we need to suppose if you have a continuous map H, and since you are to define fundamental groups at based at some point, so specifying one X naught in the space X, and you will denote the image of that as a Y naught. So I will denote this fact as H is a continuous map from X naught to Y naught. Okay. So what is our aim? That is, with respect to this continuous map, we need to set up one map from the fundamental group of X at X naught and the fundamental group of Y at Y naught. So how to do this? So our aim is to show that just we need to construct H from the fundamental group at X naught to the fundamental group of Y at Y naught by virtue of this H. Yes. So let the class F is with respect to a loop F based at X naught. Then what to do? That is, this is X and this is your Y. So you are connecting these two X naught and a Y naught by H, And if you have a loop at this, then what will be the loop at y naught? So it is very much easy to see that the loop is, so f will give you the loop H compose f. So this will be, so this is a loop in y based at y naught. So this correspondence will give you the map. So which will be, at first we will denote this map by H star, but later we will see that so we need to put the points. That is, these maps will depend on points. Okay. So X at X naught and to the fundamental group of the H star of this path of the class. Again, your exercise to
Hello, sir. Hello, sir.
Hello. Actually, I don't know what was.
Actually,
The
network was
network was
gone.
gone.
So, yeah.
Fine. Okay. So can you see this screen?
Yes.
Hello.
Yes, sir. It is visible.
Okay. 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 Fine. Okay. Fine. So the next fact is that H star depends
Sir, can you please describe previous fact?
from which one? Okay, from the
Oh,
homomorphism part.
from the yes, yes, sir. H star of class F equals to class of each composite.
This is obvious. This is actually I can leave this as an exercise. This part. This is very trivial. With the help of this, yeah, this is very trivial. You can check. I've already uh, okay prove this. Yes. So just using this fact. Okay. So H star doesn't depends not only on the map H, but it depends also on the choice of base points x naught. Yeah. So that means if suppose you consider 2 points x naught and x naught dashed, so my voice is not clear.
No, sir. It is clear.
Okay, okay, fine. So if you consider 2 points x naught and x naught dashed, two different points in the space X, then it will give rise to two different homomorphisms, even if the space is path connected, which implies that, so if the space is path connected, so you will definitely have the fundamental groups are isomorphic, but the groups are not same. Although they are isomorphic, the groups are not same group still, right? So this observation forces us to denote the homomorphism as Hx0 star. Specifying the point x0. Okay. So now, if we look at the map, then we see that so these facts that if you consider two continuous maps from one from x to y and another one from y to z, just specifying the points x0, y0 and z0 as defined previously. That is hx0 is y0 and ky0 is z0. Then you will have k compose h star. So this will be k star compose h star. So this is very easy to check. And also the identity map from the space xx0 to xx0. So for this identity map, you will have the identity homomorphism. Okay, fine. So that is I star is from this one, yes. Fine. So this is the identity homomorphism. Fine. And with the help of this, we have the following. What is that? That is, if H is a homeomorphism, if H is a homeomorphism in between x and y, satisfying the property that hx0 is y0, then is a homeomorphism of x onto y, then the homomorphism H star will become an isomorphism from the fundamental group of x at x0 onto the fundamental group of y to y at y0. Yes. So H star from this to this is an isomorphism. Yes, fine. Why it is so? Just looking at this fact, that is, if H is a homeomorphism, then you will get the continuous inverse also, which is K. Suppose K. So K be the continuous inverse of H. Then applying the previous fact, so K star compose H star, it will be K compose H star. So since K is the inverse of H, so this K compose H is I. So that means it is the I star. And similarly, just do the same thing for this one. Then you will have this J star, where J is the identity map on Y. So this fact proves that the fundamental group of X at X naught is isomorphic to okay. Hello. Hello. Okay, fine. Okay. So now we are looking for a space having non-trivial fundamental group. And interestingly, our goal is to check that the fundamental group of the circle is actually a non-trivial one, and which will be the abelian group of integers. But I will give you the proof by introducing the covering spaces. So I have already mentioned that. So you can compute fundamental groups using covering spaces, and another one is that using deformation retracts. Interestingly, we will do this by using our familiar spaces and their fundamental groups. Yes. So now we are looking for the notion of covering spaces. Covering spaces to compute fundamental groups of topological spaces. We have already observed that any convex subspace of Rn has a trivial fundamental group, and which involves okay, fine. I'll not get into that. Okay. So let us first define covering spaces. Yes. So let us define. The definition will be like that. That suppose if you have a map P from a space E to B, a continuous surjection, a continuous map, continuous surjective map. Okay. So suppose you have a continuous surjective map from the space E onto B. Then an open set U in B is said to be evenly covered by P if the inverse image P inverse U can be written as the union of disjoint open sets V alphas in the space E. Yes. That means if you can express this inverse image of the set U as union of V alphas, where V alphas are disjoint open sets in the space E, such that for each alpha the restriction map P to the set V alpha is a homeomorphism. From V alpha onto U. That means if you can express P inverse U as the union of disjoint open sets V alphas in E, where V alphas are homeomorphic to capital U. So that is V alphas are homeomorphic to capital U. So that means suppose okay, fine, yes. So this is the U. So then you will have so these things are homeomorphic to this. Yes. That is, if you sit on any of this space, you will, if you look at the, if you look downwards, then you will see that the same thing is here. So that is why these V alphas are defined to be a partition of P inverse U into slices. Okay. Yes. So, for example, okay, let us consider the map from R to S1. So that actually I intentionally introduce this map because this is this meets our requirement to show that the fundamental group of S1 will be non-trivial. So this P defined by suppose P of T is equal to e to the power 2 pi I t. Okay, this one. Fine. Then yes. So now consider the open set, this one. Yes, this one. That is, this is your U. Suppose this is U. U is the set of all xy such that x is greater than 0, or you can write it as this, where cos of 2 pi t is greater than 0. Then what will be your P inverse u? What will be your P inverse u? That is, set of all those t belongs to R such that P of t belongs to u. That means set of all t belongs to R. So P of t is e to the power 2 pi I t. So that belongs to u means if cos of 2 pi t is greater than 0. So that means what is the set? Okay. So this is actually here. So union of this, where n belongs to z. You can check this on your own. That is, if I draw the line, that is, so this is 0, this is 1, 2, this is -1, -2. Then these intervals. -4, 1/4. This will be yes, and so on. So you can denote these intervals as, suppose it is Vn. So Vn is n minus 1/4, n plus 1/4 for all n belongs to Z. Then your P inverse U is union of Vn. Okay, fine. So now, since on each of these intervals, actually, if you consider the closed interval also, then you will see that the function t to sine 2 pi t, it is actually a strictly increasing, monotonic increasing function. So that is why the map is 1, 1 on these intervals. And also by using the continuity, you can say that this P will map actually onto U bar. So that means this P is a homeomorphism because this is compact space. So you can definitely say that P is a homeomorphism from Vn bar onto U bar. And in particular, that is, it is a homeomorphism from Vn onto U. So these Vn's are homeomorphic with u by the restriction of P to Vn. So this implies this U is evenly covered by P. And these are the slices, Vns. Okay, fine. So if you consider this U, then you can have this. Now, if you consider, suppose this one, then using the same arguments, and you can check that P inverse U is again will have the same property. And if you consider the lower half ones and the left and right half ones, sorry, this is the left, so you can have this one. Okay, fine. So these open sets will cover the circle S1. Fine. And this P actually it will be a covering map. And what is a covering map? The definition is like that. Just if you consider a one continuous surjection from a space E onto B, then this P is defined to be a covering map if every point B belongs to capital B has a neighborhood U which is evenly covered by P. Which is evenly covered by P. Okay. And in that case, E is called a covering space of B. So if you have a covering map, then you can say that the domain space is a covering space of the codomain space. And the certain facts are that, so these facts can be recorded which are like that okay, yes, if P be a covering map, then for any B belongs to capital B, P inverse B is discrete. P inverse B is discrete. That means, that is, suppose this is your B and this is your X, this is your E. So it is B, so you have this 1. So yes, yes. So these are slices. This is your P inverse U. So then P inverse V, so if you intersect P inverse V with each slice V alphas, then you will see that each slice will contain exactly one point that map to B. Since each slice is homeomorphic to the open set U. Yes. So that is why each P inverse B is discrete. Okay. Now fact 2 is that if you consider a covering map, then you can check that. So if P be a covering map, then it must be an open map. So this can be treated as an exercise. So any covering map is an open map. Yeah. Also, you can check that okay, just you have a space X and IX be the identity map. Then obviously IX is a covering map. So you do not have any difficulty. Also, just consider this space X Cartesian product with this one. That is n copies of X. Then the map defined by this goes to X. So this will be a covering map. Just you can have this very easily. Okay, fine. And what we are expecting that this theorem that I have already talked about, the map from R to S1, that one defined by this. So this is a covering map. That is, R is a covering space of S1. Since if you consider any point on the circle, then that point will lie on any of the open sets that I have specified. And that open set and its inverse of that open set with respect to P will be union of the VNs. And each VN is homeomorphic to the open set. So that is why, so with the help of this observation, you can say that this P is a covering map. Now, if you consider the same map, but you restrict the domain space from R to the set of all positive reals. That is, suppose P be the map from R plus to S1 by the defined by the same rule. Then this is a continuous surjective map. Now, just taking the point x naught is 1, 0. Then this x naught has no neighborhood u which is evenly covered by P. As if you consider a typical neighborhood u on the circle, suppose this is your x naught. So then okay. So this u will give you that P inverse u will be some 0, delta union. Okay, you can take this as, you don't need to take this one, sorry. Just take one of this, yes. Any typical open set, yeah. This part. Then P inverse u will be this one. Union and this. And each of these intervals is homeomorphic to u by P. But what about this one? This interval will not be homeomorphic to u. It will be embedded in u. So for that reason, you can say that this is not a covering map. So this indicates that if you restrict a covering map, then that may not be a covering map. Okay. Okay, but yes, the observation is that locally, if you think this map locally, then you will see that this map is actually a local homeomorphism of R plus onto S1. What does it mean by local homeomorphism? That is, a map from X to Y is said to be a local homeomorphism if each point of the domain space has a neighborhood which will be mapped homeomorphically onto an open set of the codomain space. So for that reason, this P is actually a local homeomorphism, and you can check that. This is a question. You can check that every covering map is a local homeomorphism. Local homeomorphism. But the converse is not true, as you have seen already this one. This is a local homeomorphism, but it is not a covering map. Okay. Fine. So I think now it is 5:30. So okay. Yes. Okay. I should stop today. Yeah. And in my next lecture, I will be talking about the lifting correspondence of paths and lifting lemma also. Yes. And with the help of this, I can easily find out the fundamental group of the circle, and which will be the group of integers. Yes. Which one? Auditro, Roy? The last one. You can check easily. This part is, this is 1 minute. What is happening? Network is creating a problem today. The interval 0 delta, yes. This will be embedded in U. It will not cover the whole interval, whole open set U. It will be the upper half part of U. Given a topological space, does there exist a covering space other than itself? Okay. Good question. Yeah, I think, okay. So you are saying that does there exist a covering space other than itself? So, okay, okay, fine. Right here. Okay. No, I don't know. The pen is not working. Why? Every 1 point space. What is that? He is asking that given a topological space, does there always exist a covering space other than itself? I think Actually, you need to have a continuous surjection first.
Sir, hello.
Yes.
Uh, if we choose a one-point space,
Yes.
okay, then for that we can consider any space
Mm-hmm.
and took the constant map,
Yes.
any con. Okay, then
Hmm.
this will be obviously a covering map.
Hmm. Yes.
Mm,
This will be a
Covering map.
yes covering map. Okay.
Okay, so
Okay. So the one point space. So for any topological space, you are saying that the one point space is a covering space of that space.
yes.
Some other examples. Okay, that we can take into consideration for our next lecture. Yes. Okay. That is a good question. Yes, surely. Universal cover. Yes, yes, yes. With some conditions, right? That is a good question, and actually, my student Rana has already posed this question to Professor K. Gangobadai in his first lecture. That what was your question, Rana? That for a given space X, can you define a space whose quotient space will be that space, right?
Yes, sir. Exactly.
Yes. So the same.
Actually, if we have a space, so we can construct another space from by the quotient map or partition. Okay, so even if we look the, for example, if we look from a rectangle, we can construct a torus. Okay, or obviously for a rectangle, from a rectangle we can construct a sphere. So
Yes.
conversely, we also uh, have shown on that lecture of Krishnendu sir, so that from a sphere we can also find a rectangle.
Yes.
Okay, so that's why that's why the question was arrived from in my mind that for any topological space, can I find another topological space for the such that the old space will be a quotient space for new space.
Yeah, quotient spaces are actually, so that is why these are very interesting and important.
Yes, obviously, this is very interesting.
Yeah. Yeah. So Devabroto Babu, we will looking for this one for our next lecture. Okay. Actually, during my lecture, I need to admit pupils. So that is why that creates a problem actually. Okay. I think no questions is there. So shall I stop, Sumanto?
Okay, sir.
Yes, sir. Yes, sir.